Hi everyone! Thank you for taking the time out of your day to be here today. My name is Gabby Signetti. I am a product line manager at MSA Safety, working on the FieldServer Gateway product line. FieldServer Gateways have been a trusted solution in the connectivity and automation space for over 25 years now, helping companies bridge the gap between legacy protocols and modern technology. Today, I'll be talking about bridging legacy Modbus devices with modern IoT architectures, a critical topic as industries continue to modernize and connect their existing infrastructure to today's advanced IoT systems. I'm excited to share insights, best practices, and real-world examples with you all. So let's get started. Here is a brief overview of the agenda for today. I will start by providing an overview of Modbus, a legacy but still growing protocol, as well as more modern protocols like MQTT and OPC UA. I will discuss how to bridge Modbus to IoT platforms, common pitfalls and best practices in doing so as well. I will also introduce the Modbus IoT Gateway and its key product features and use cases. Then I will leave time at the end to answer some questions. So let's get started. In the world of industrial automation, communication is everything. Devices need to talk to each other, clearly, reliably, and often across great distances. One of the earliest and still one of the most important protocols that made this possible is Modbus. The Modbus protocol was created in 1979 by a company called Modicon, the inventors of the programmable logic controller, also known as the PLC. Back then, automation systems were growing fast, but manufacturers often used proprietary methods that did not work well together. Modicon developed Modbus to provide a simple, open, vendor-neutral way for devices to communicate, especially over serial lines like RS-232 and RS-485. It used a master-slave architecture where one device would request data and the other would respond. Through the 1980s and 90s, Modbus became the de facto standard in industrial automation, especially in SCADA systems, manufacturing, utilities, and energy sectors. Its simplicity made it easy to implement, and its open standard meant it could be used by anyone without licensing fees. Two common serial formats emerged, Modbus RTU and Modbus ASCII, which is a human-readable, but it's a little less common. In 1990s, Modbus evolved. As Ethernet became more common in industrial environments, Modbus TCP/IP was introduced. This brought Modbus into modern era, allowing it to operate over Ethernet networks using TCP/IP, making it faster and more scalable. In 2004, the Modbus organization was formed, a nonprofit group to maintain and promote the protocol. Since then, Modbus has continued to adapt. It's been integrated into wireless networks, IoT systems, and even cloud platforms, often through gateways and protocol converters. It's still widely supported by nearly every industrial manufacturer today. So why has Modbus lasted more than 4 decades? It's simple, it's reliable, it's open, and it works. That's why. Whether it's an old PLC from the 80s or a modern IoT gateway, Modbus continues to bridge the gap of generations of technology. From its origins in 1979 through the rise of Modbus TCP and into the ages of Industry 4.0, Modbus has proven itself as one of the most durable and adaptable protocols in industrial automation. And even in a world of newer, more complex standard, Modbus reminds us that sometimes simplicity wins. Now, let's take a closer look at why Modbus was not designed for today's industrial and IoT needs. First and foremost, Modbus has no encryption and no authentication. This means that the data being transmitted, whether it's temperature readings, motor speeds, or control commands, is sent in plain text. Anyone with access to the network can intercept, view, or even alter that data, and there's no way for devices to confirm that they're talking to a trusted source. In today's world, where cybersecurity threats are real and growing, that kind of vulnerability just doesn't cut it. This might have been fine in an isolated, air-gapped industrial networks 20 years ago, but it's a major concern in industrial, new growing, modern IoT environments. Next, Modbus is a polling-only protocol. This means that devices can't just send data when something important happens. Instead, the master constantly has to ask, "Do you have any new data yet?" over and over again. It's like checking your mailbox every 5 minutes instead of getting a notification when a new letter arrives. This leads to inefficiencies, unnecessary network traffic, and most importantly, missed opportunities for a real-time response. If something critical happens between the polling intervals, this means that the system may not catch it in time. Another limitation that Modbus doesn't use is structured data models. What you are getting are just raw register values, basically just a bunch of numbers. For example, register 4001 might just be a temperature value in Celsius, but Modbus does not tell you that. There's no metadata, no labeling, no hierarchy, nothing to explain what the data means. This makes it hard to scale, especially because every new integration requires someone to manually define and interpret those registers. There's no self-describing data, which modern systems rely for interoperability. It also was not built for the internet or IP networks originally. There's no native support for cloud protocols, no encryption, no session management, and no way to handle connectivity loss gracefully. So if you want to push Modbus to something like AWS, Azure, or any modern analytics platform, you're going to need an additional layer of infrastructure to translate that secure data. To sum this up, while Modbus is simple and easy to implement, it was never meant to be secure, scalable, or internet connected. It's great for legacy systems and basic device communication, but when it comes to modern IoT architectures, Modbus just doesn't meet the requirements out of the box. And that's why in many modern environments, we need solutions that bridge this gap and bring legacy systems into a modern world. Now, let's dive into a key part of any modern industrial connectivity strategy, the gateway. Think of the gateway as a translator, but also as an enhancer. It sits between your industrial equipment and your IT systems and plays a critical role in making that connection not just possible, but secure, efficient, and scalable. Let's break this down. First, translation. Many of the machines out in the field today, whether it's a PLC running a manufacturing line or a controller managing HVAC systems in a commercial building, speak protocols like Modbus, BACnet, or Profinet. These are field protocols that were never designed to connect directly to the internet or to cloud platforms. That's where the gateway comes into play. It converts these legacy protocols into modern interoperable formats like MQTT or OPC UA. These are the languages of modern industrial IoT. They're lightweight, efficient, built for scalable data exchange. So instead of asking OEMs to redesign their hardware or speak MQTT or asking integrators to rewire and reprogram their hardware and legacy devices, the gateway handles it for you. It's a protocol translation, but done intelligently and without any disruption to your existing systems. Second is enhancement. The gateway doesn't just convert formats, it adds value to the data itself. First, it adds encryption and authentication, so the data isn't just moving, but it's moving securely. That's absolutely critical when you're dealing with industrial operations, where even minor tampering can lead to big consequences. Second, it applies to data modeling. Instead of sending raw, unstructured data values, the gateway can structure and contextualize that data. It understands that a value from Modbus, register 4001, might represent temperature in Celsius or a fault code or a pressure reading and can label it accordingly. This modeling makes it much easier to interpret and use the data further downstream, whether that's in a dashboard, a SCADA system, or a machine learning model in the cloud. Next, let's talk about publishing. Once the data is translated, secured, and structured, it's ready to go whenever it's needed. The Edge Gateway can help publish it to the cloud, to a local SCADA system, or even to a local edge compute resource for real-time analytics. It supports flexible architectures, centralized, decentralized, or hybrid, depending on what your application needs. This means that you're not just unlocking data, you're unlocking new ways to use it, to see it, to visualize it. So what does this mean for you? If you're an OEM, You don't need to redesign your entire controller lineup. You can keep shipping your existing products. The gateway just takes care of the connectivity and security layers. If you're a system integrator, you can keep using your customer's legacy devices and service. You don't have to replace every controller in the plant to start sending data to the cloud or performing analytics. That gateway device might have been installed 10 years ago, but now thanks to a gateway, it can communicate like a modern smart device. And importantly, you get all of this without compromising cybersecurity, big upgrades, or interrupting production. In short, the gateway turns your existing equipment into cloud-ready, secure, intelligent devices without touching the hardware. It's modernization without a lot of disruption, and it's one of the most cost-effective and scalable ways to upgrade from a legacy system to a digital age device. Now, let's talk about MQTT, the protocol for IoT. In today's connected world, industrial systems aren't just automated, they're networked, often across wide areas and unreliable links. Enter MQTT, a lightweight, publish-subscribe protocol built for exactly that challenge. Originally designed for oil pipelines, MQTT has grown into one of the most popular messaging protocols for the industrial Internet of Things. MQTT stands for Message Queuing Telemetry Transport, and it was created in 1999 by Andy Stanford Clark of IBM and Arlen Nipper of Archon, which is now Eurotech. Their goal was to design a communication protocol that worked reliably over low bandwidth, high latency, or unreliable networks, like those found in remote oil field telemetry. They based it on the publish-subscribe model, which is highly efficient. Instead of devices polling for updates like Modbus, they subscribe to topics and receive only the relevant messages. In the early 2000s, MQTT quietly found success in energy, oil and gas, and telecommunications, where constrained bandwidth and high uptime requirements made traditional protocols impractical. It was also perfectly suited for embedded devices and mobile networks, thanks to its tiny code footprint and low power usage. The protocol really began to take off after IBM released MQTT as an open specification in 2010, and then contributed it to the OASIS standards body in 2013. In 2014, MQTT 3.11 became an official OASIS standard, and the protocol gained mainstream traction in everything from home automation to industrial control systems. Today, MQTT is everywhere, from factory floors to cloud platforms. It's a key protocol built on Industry 4.0, connecting sensors, edge gateways, and cloud services like AWS, Azure, and Google Cloud. With the release of MQTT 5.0 in 2019, it gained more robust features like improved error handling, message expiration, and user properties, making it more powerful for enterprise-scale systems. Now that it was created in 1999 and now it's 25 years old, MQTT has become the backbone of many modern industrial and IoT systems. From building automation and energy metering and manufacturing and water utilities. Why? Because it was designed for this implementation. It's well understood, it requires no certification, and it's lightweight enough to run on embedded processors. It's also widely supported across platforms and vendors. MQTT's strength is its focus. It does one thing and it does it very well. It doesn't try to replace complex protocols like OPC UA or Modbus. Instead, it complements them by connecting devices, systems, and cloud platforms in real time over any network reliably. In a world that's getting more connected by the day, MQTT is one protocol that's not just surviving, it's thriving. Now, let's take a moment to talk about OPC UA, one of the foundational technologies driving modern industrial connectivity. OPC UA, short for Open Platform Communications Unified Architecture, was introduced in 2006. Today, it's not just another protocol, it's become a global industrial standard, adopted across factory automation, process control, power and energy, pharmaceutical manufacturing, and increasingly industrial IoT platforms. Why has it gained so much traction? Because OPC UA isn't just about moving data. It's about moving structured, meaningful, secure data in a way that machines and systems can actually understand and trust. First and foremost, OPC UA was designed from the ground up for industrial use. It supports a wide range of industrial equipment and use cases, from PLCs on a factory floor to enterprise manufacturing execution systems. It's platform independent, which means that it works really well on Windows, Linux, or other embedded controllers. And critically, it's vendor neutral. You don't need to lock yourself into one system, one ecosystem. That's a big reason why it's become the standard interface for interoperability between machines and systems. Now, what really sets OPC UA apart is its focus on structured data and object modeling. This isn't just about sending values like temperature equals 72. OPC UA allows you to model real-world systems like pumps, motors, or production lines as objects with properties, relationships, behaviors, and hierarchies. This rich data modeling makes it easier to build context-aware systems where machines not only exchange data but actually understand what they mean. It's incredibly powerful for creating digital twins, standardizing device profiles, and interoperable interfaces across vendors and verticals. Another major advantage of OPC UA is its native security. It was built with security in mind from day one, and that includes encryption of data in transit, user and role-based access control. This means that you're not just getting data from point A to point B, you're doing it securely and in compliance with cybersecurity standards. This makes OPC UA a natural fit for plant-wide or even global enterprise deployments where both data integrity and access control are critical. Now, how does OPC UA compare to MQTT, you might be wondering? It's a good question. Think of MQTT as the fast lane to the cloud. It's simple, it's lightweight, and it's highly efficient. Perfect for pushing data quickly to the cloud platforms, especially when the bandwidth is limited. By contrast, OPC UA is a more structured pipeline across industrial systems. It excels in scenarios where you need context-rich, secure, and standardized communication between devices, PLCs, and enterprise systems. In many modern architectures, these two protocols actually complement each other. OPC UA provides a structured, secure data at the edge, where MQTT handles efficient transport to the cloud, and when used together through an edge gateway or a unified data platform, they enable true end-to-end industrial connectivity. So, to sum it up a little bit more, OPC UA is a mature, secure, and highly designed structured protocol. It's designed for the industrial automation, and it's key for this market. Before we dive into solutions, first let's look at common pitfalls we see when bridging legacy modern devices to modern IoT systems like MQTT and OPC UA. Understanding these helps us avoid downtime, data chaos, and rework later on. The first would be assuming that Modbus is secure. This is probably the number one misconception, that Modbus is somehow secure because it's old or running on a closed network. In reality, Modbus has no built-in security, no encryption, no authentication, like we mentioned before. So if you're exposing Modbus traffic over IP, especially public networks, you're wide open to threats. That's why your gateway should provide TLS encryption certificates or access control from the edge. Security should be designed in, not just assumed. Next would be sending raw, unstructured data. Another big pitfall is pushing raw Modbus registers straight into your IoT system without context or structure. You'll get a message like 40002 equals 1245. But what does that mean, right? A temperature, a voltage, a fault code, I'm not sure. So without the structured data labeled and tagged, you'll waste time decoding it later. Use MQTT with JSON payloads or OPC UA models to give your data meaning from the start. The next one would be overpulling or overloading those devices. We see often that teams pull Modbus devices way too frequently, thinking more data is better. But Modbus is a polling-based device. It's on a shared bus protocol, so over-polling can actually clog the network, cause errors, or crash legacy devices. Instead, we want to configure the data to publish data only when it changes or crosses a certain threshold. And that keeps bandwidth low and the performance high. Next would be hard coding register maps. Hard coding the Modbus register mappings directly into firmware or scripts might seem quick, but it's actually a maintenance nightmare. It makes your deployment rigid, error prone, and very hard to scale. A better approach is using importable templates or visual configuration tools that make updates and reuse a lot easier. Next would be ignoring bandwidth or latency constraints. If you're sending high-frequency Modbus data over networks like LTE, satellite, or even shared VPNs, the bandwidth becomes a real constraint. You might experience delays, drop data, or even high cellular bills. Your gateway should handle this by applying edge filtering, compression, or smart buffering to optimize data flow. The next one is no remote access or updated strategy. This is very concerning because if you're deploying gateways in remote sites and realizing that it's too late, that you can't upgrade or reconfigure them without going on site, that will be a very hard issue for you in the future, because every IoT deployment needs a secure way to manage devices remotely. Without this, scaling your deployment is very, very difficult. Next would be skipping the pilot phase, and we've seen a lot of teams roll out 10 sites with 200 devices only to discover basic mapping issues or data flow problems. So we want to always test your device, start small, test your mappings, verify the connection, and then you can scale. The good news is that every one of these pitfalls is avoidable, and with the right planning, a smart Modbus gateway or a structured rollout can help you bridge even the oldest legacy devices into a modern, scalable IoT system. So now let's take a look at some best practices for bridging Modbus systems into the IoT world. First would be to choose a configurable protocol translation IoT gateway. The first step would be to choose a gateway that's actually built for this kind of work. That means it needs to support Modbus, particularly hopefully RTU and TCP, and support for systems with modern IoT protocols like MQTT, and if they're going more in the industrial route, OPC UA would also be very helpful for that data exchange. But it's not just about protocols. The gateway should also be easy to configure, ideally with a web interface with a low-code environment. Even some pre-built templates for popular Modbus devices can save hours of manual work. I do want to mention that MSA Safety's new Modbus IoT gateway was built with all of these best practices in mind. I will go over more about the Modbus IoT gateway in the following slides, but I do just want to point that out, that we do have access to a really helpful graphical user interface, and it also has access to Modbus, MQTT, and OPC UA. The next best practice would be to understand and map the Modbus registers. Modbus is very simple and widely used, like we mentioned, but it has no metadata, right? So you need to know in advance exactly what each register means. For example, register 4001 might be temperature, register 4002 might be RPM, and so on. You also need to know the data type, scaling factors that come into play, etc. So this is where a really good device map or template becomes critical, especially for OEMs and integrators that are working with multiple devices across multiple sites. The next one would be to structure and label data for context. Once you've pulled the raw Modbus data, don't just pass it through unchanged. Use the gateway to add structure, labels, and you can name the data as well. Why? Because cloud platforms and analytics tools need context. If all they get is register 4001 equals 72, that's not helpful. You need to convert it into temperature Celsius equals 72. Now that's actionable, and that means that anyone sees the platform can know that that's what that register means. Many gateways let you apply tags, units, and JSON formatting for outgoing data. If you're using OPC UA, you can even apply full object models. This makes your data easier to integrate SCADA platforms, cloud analytics, and digital twins, and avoids a lot of downstream confusion. Next one would be to add security. TLS certificates and access control, like we've mentioned before, it's a critical piece and is often overlooked. Modbus as a protocol is not secure, that we mentioned before, and you want to look for gateways that have these security built in just to protect yourself from outside threats. And the last one would be enabling remote management. Once your gateways are deployed, especially in the field, you'll want to be able to monitor and manage them remotely. That includes updating configurations, pushing firmware updates, and diagnosing issues. Many gateways now support cloud-based fleet management, which is a huge lifesaver, especially for system integrators working across a dozen remote sites. So in summary, bridging the Modbus to IoT is very doable, even with legacy systems, but doing it well means focusing on three main things. Using the right gateway that was designed for this purpose, transforming raw data into structured, secure insights, and having that security management as well. With these best practices, you can unlock real-time visibility, predictive maintenance, and cloud integration, all without touching your existing hardware. I'm excited to introduce MSA's new FieldServer gateway, the Modbus IoT Gateway. It's designed to bridge legacy Modbus devices to modern IoT systems using protocols like Modbus RTU, ASCII, and TCP/IP, MQTT versions 3 and 5, and OPC UA. The gateway comes in 4 hardware variations so that you can choose what best fits your product or environment. The first one is 2 serial ports and 1 Ethernet port, great for basic Modbus networks. The second one is 2 Ethernet ports and 2 serial ports, which is ideal if you need to separate the subnets. The third is a Wi-Fi version, 1 Ethernet port and 2 dual serial ports for wireless setups. And the next one would be Wi-Fi and cellular, 1 Ethernet port and 1 serial port, which is perfect for remote or mobile sites. But beyond the hardware, the special sauce is really in the software, which is where the configuration happens and the connectivity happens as well. Each gateway includes a user-friendly graphical user interface with configurable templates and reusable profiles. These tools save so much time, cut costs, and reduce human error, especially for multiple deployments. The gateway has also built-in diagnostic tools such as diagnostic captures, detailed system logs, real-time status monitoring so that you can spot and fix issues early. Plus, with the cloud-based FieldServer Manager, you can remotely access and configure devices, update your firmware, and set SMS and email alerts whenever something goes into alarm. This is perfect for users and facility managers that are handling many devices. To give a quick summary, the Modbus IoT Gateway bridges those legacy devices to the cloud through MQTT, OPC UA, offers a flexible hardware variations, an intuitive graphical user interface, powerful diagnostics, and remote management, helping you connect, configure, and manage your devices with confidence. I do want to highlight key features in the Modbus IoT Gateway platform that I find very useful for even novice users and truly sets this platform apart. First would be the smart dynamic configuration experience. The platform only asks you for information that's relevant to the setup that you're currently working on. For example, if you're configuring a Modbus connection, the system automatically detects that and only shows fields specific to Modbus. Nothing more, nothing less. It's intuitive and it minimizes confusion, especially for users who may not be protocol experts. Now here's something that makes life even easier, especially when you're working with Modbus. Let's say you're pulling Modbus registers info for information from a device manual or an Excel spreadsheet. You can copy and paste that data directly into the GUI, and that system will auto-populate the required fields based on the data you inputted. Things like address, data type, function code, and more. This means that even a novice user can be guided step by step through the configuration without having to constantly guess or refer to documentation. Next would be the real-time validation and feedback. Another key feature is a real-time feedback, like I mentioned. As you can connect your device, the graphical user interface displays these live values reading from the field device in real time, so you know immediately that your device is working. If anything is missing, misconfigured, or incorrect, the system highlights it in red and walks you through what exactly needs to be fixed to complete a valid setup. This kind of immediate validation helps you catch mistakes early and dramatically reduces the time spent troubleshooting during commissioning. Another key feature that I love is there is contextual help at your fingertips. Since there's a lot of niche information that goes into configuring devices, MSA makes it easier by providing contextual help. This means that when you're not sure what something means, click on the information icon in the toolbar and a quick explanation will come up. No need to dig through documentation. For example, if you're not sure what pull delay means, click on the icon and a blurb will pop up. Next is the actionable data. We know how painful it can be working with hard-coded Modbus registers. That is why this platform includes tools that lets you label, organize, and manipulate your data, turning raw register maps into actionable, meaningful information. This is especially important when you're scaling, or maintaining multiple systems. In the example below, we want to read a voltage and frequency from a PM500. However, these values are scaled by a factor of 100, which can lead to results that appear incorrect or meaningless during setup. By using the built-in data manipulation tools, we can easily divide the values by 100, providing real-time, accurate, and meaningful data. As you can see here, the voltage clearly reads as 232 volts and the frequency is 50 hertz, exactly as expected after applying proper scaling, and it makes sense. The last set of features that I have to mention are the profile editor and instance editor capability on the graphical user interface. This means that you can have templates that you can reuse across projects, saving time and reducing manual entry. So let's say you're setting up multiple gateways across several buildings and each one need to pull data from the same type of power meter, maybe a PM500 or a similar device. Rather than configuring each gateway from scratch, you can use the profile editor to create a template that includes all the necessary points, data manipulation, and communication settings. Then, with the instance editor, you can apply the profile to each new gateway, adjusting only the unique details like IP address or device ID. That way, you can reuse the configuration, reduce manual input, and ensure consistency across all deployments. This graphical user interface also comes with powerful diagnostic tools like diagnostic captures, system logs, and health checks to help you find and fix issues early. And lastly is the remote monitoring and management side of it. Like I mentioned with FieldServer Manager, that means you can remotely manage your device from anywhere. If you are someone that works for or you own a plant that's an hour away, you can get SMS or email notifications when something is an alarm and something is going wrong. Why does all this matter? Because together all of these features make a configuration faster and smarter. It minimizes risk of errors and gives you meaningful data that's easier to manage. Now that we have talked a lot about modernizing legacy systems and the Modbus IoT Gateway, let's discuss a few common use cases that we see this product being a great fit for. First, we have an OEM that's been selling trusted industrial controllers for years. Their devices run Modbus, which is still reliable, but not built for the cloud like we mentioned. They want to offer remote monitoring and IoT connectivity, but without redesigning hardware or going through recertification. So instead, they added our Modbus IoT Gateway. Now, their devices speak MQTT or OPC UA, enabling real cloud integration, all with zero redesign. Next, we have a system integrator working with a water utility. The utility's pump stations still use Modbus RTU over dial-up lines pulling every 15 minutes. It was slow, unreliable, and very expensive. The integrator deployed our MSA gateways at each site, connected over LTE. Now data streams in real time via MQTT with only meaningful changes pushed, reducing cost and increasing visibility. Operators can now monitor systems from a tablet, dashboard, or even their phone. Lastly, Let's say we are looking at a manufacturing facility going through digital transformation. They're moving toward Industry 4.0 and standardizing on OPC UA, but many subsystems still use Modbus. Instead of replacing everything, they used our gateway to convert Modbus data to OPC UA, enriching it with data models and securing it with certificates. Now they have a unified, secure view across their entire plant without disrupting production. In each case, OEM, integrator, and manufacturer, the challenge was the same. Legacy Modbus devices holding back progress. But with the Modbus IT Gateway, they were able to modernize without redesign, connect securely to the cloud or edge, and unlock new digital value from existing assets. That's the power of simple, scalable modernization. And this is how we help bridge the gap between legacy and opportunity. To wrap things up, successfully bridging legacy Modbus devices with modern IoT architectures requires more than just connecting hardware. It demands partnering with a gateway solution that's truly IoT ready and supports the leading protocols in the market. By choosing the right gateway, you ensure seamless integration, streamlined configuration, meaningful data insights, and reliable remote monitoring. Okay, now to answer some questions. I see a question that says, what is the long-term outlook for Modbus in Industry 4.0? That is a great question. It's also one of the most common questions that we do get, and honestly, one of the most important. The reality is Modbus is not going away anytime soon. It's been around since the late 1970s and is still embedded in millions of industrial devices worldwide, PLCs, sensors, drives, meters, you name it. The reason is that it has survived this long is because it's simple, it's reliable, and well understood. Engineers know it well, the plants trust it, and it just works. But in the context of Industry 4.0, the role of Modbus is changing. It's no longer the protocol that runs the entire architecture. Instead, it's becoming more of a data source within a larger ecosystem. Think of it as a foundation. It feeds a critical machine level data into modern platforms where analytics, visualization, and decision making happen. So what does this mean for the long term? We don't have to rip and replace. Instead of discarding valuable Modbus devices, organizations can use gateways and edge solutions to integrate them into cloud and enterprise systems. It shifts the roles from control to insight, so Modbus isn't just running the plant anymore, it's feeding the data that allows smarter systems to optimize the plant. It also extends ROI. So companies protect decades of investment while still modernizing the operations, which I think is great. The bottom line here is Modbus is here to stay, but it's a job description that is evolving. So in Industry 4.0, its value comes from how well you modernize integration, not from just replacing it outright. Okay, next question. I see a question that says, how do you handle scalability when integrating many Modbus devices? So scalability is where projects either succeed or stall out. It's one thing to connect 10 devices for a pilot project, but it's another to connect hundreds and hundreds across multiple sites. So here's a challenge with Modbus is that it is a polling protocol, like I mentioned today. That means the master has to ask each device for the data, and if you're not careful with this, the network does slow down and latency increases and the data freshness does suffer. So how do we scale Modbus is avoid one-to-one integrations. Point-to-point works very good for small setups, but it doesn't scale. So use gateways that act as aggregators, handling dozens or even hundreds of Modbus devices at once. Group the devices logically, so organize them by process, site, or line. That way you can manage them as a block and not individually. I would say next would be to push data into brokered systems like MQTT. So once the data is in MQTT, the number of subscribers doesn't matter. You can add dashboards, analytics without having to touch the Modbus devices again. And also use gateways that are really good with load management. The best gateways optimize polling cycles, prevent overloads, and can prioritize certain devices or registers when bandwidth is tight. This way, adding a new device or even a new plant doesn't require rebuilding an architecture. It's kind of plug and play. So yeah. All right. I see another question for how does latency affect Modbus and IoT systems? Great question, because latency is often overlooked until it becomes a big problem. So the truth is that Modbus, as we know, was not built for high-speed real-time applications. It's perfectly fine for equipment monitoring, but it's just not ideal for high-frequency motion control or very fast safety interlocks. With that said, most IIoT platforms and applications, the latency tolerance is a lot higher. For dashboards, predictive management, and cloud applications, even multi-second delays are usually acceptable. Nobody's shutting down a turbine because the data took an extra half second to arrive. But you do need to be careful when the device count is very large, because pulling hundreds of devices on a single bus can increase those delays. I would also say that the long distance communication, adding hops and cloud can add latency as well. And also control loops. If you're feeding Modbus data into a control system that expects real-time feedback, you may run into issues here. The solution overall, to answer your question, would be to push sensitive time function to the edge. Let gateways or controllers handle real-time logic, and then forward aggregated data to the cloud at an acceptable, manageable pace. Therefore, latency is not a big deal breaker. It's more about putting the right data in the right place at the right speed. Alrighty. Next question. Does the Modbus IoT Gateway support AWS and Azure? I would say that it's going to support AWS and Azure in the near future, and we're very excited to be able to connect to these cloud platforms. So keep your eye out for the Modbus IoT Gateway product page and blog for updates with the product. Next question. How do you troubleshoot Modbus communication issues? Good question. This is the part like no one loves to talk about, but it's where projects can lose most of the time. So it usually comes down to a few different aspects. I would start with physical layering issues, RS-485 wiring, termination resistors, grounding. These are classic culprits. A loose connection can mimic a software bug and waste hours of effort. Next, I would say register mapping errors. Every vendor has its own register map, so misreading the manual or mixing up data types can cause values to look very wrong. You don't want your temperature to look like it's at 300 or 1,000 degrees. And then also, I'd say polling overload. If you request too much data too quickly, devices cannot keep up. So this leads to timeouts, missed packets, or slow responses. The good news is a modern gateway can help here with the built-in diagnostic features, auto discovery, which is where you can automatically identify registers, reducing the human error, logging. This helps you pinpoint whether issues wiring, configuration, or network load. But yeah, troubleshooting is never very glamorous, but it's really important to have the right tools to help you figure out what the problem is. All right, next question. How can Modbus help with sustainability initiatives? This is a great question. Modbus devices, even though they're decades old, are often the first place to find sustainability data. They track energy use, runtime hours, cycle counts, temperatures, pressures. When you can aggregate this data, you can identify the equipment consuming excessive energy, optimize production schedules, and to minimize idle time. For example, a water treatment plant using legacy Modbus meters can be able to reduce energy by X amount of percent just by analyzing the pump runtime data and adjusting those cycles. So yeah. All right. Next question, is Modbus safe to use in mission critical systems? The short answer is yes, but if you want to treat it, you have to treat it the right way. Modbus itself is not super secure, Like we mentioned before, it doesn't have the encryption, authentication, but that doesn't mean that it can't be used safely, right? So you have to, you need to build safeguards around it. For mission critical systems, like you mentioned, the best practices would probably be segmentation. Keep Modbus devices isolated from the networks, not on enterprise LAN. Use gateways that have secure encapsulation, TLS certificates, tunneling, etc. You want to always have a fallback path or duplicate gateways to avoid a single point of failure. And then watch out for unusual traffic too. Modbus can't stop an intrusion, but it can detect it at the network level. So I would say while Modbus isn't inherently secure, a properly designed architecture can absolutely make it safe enough for mission critical devices and reporting. Okay, another question. What industries still rely most heavily on Modbus? I would say so many different industries, but I will mention the ones that come to my head are utilities, power distribution, smart metering, oil and gas, and in the oil and gas are like the pumps, flow meters, pipeline monitoring. I would also say manufacturing, like robotics and sensors, as well as the building automation, HVAC, lighting, security systems, and transportation, like train systems and elevators. So yeah. All right. I will say, I think we have time for maybe one last question. I'll take, how do you balance modernization with legacy support in industrial projects? I think this is a big challenge for industrial organizations. The truth is you can't modernize everything overnight, so plants run on tight schedules, downtime is expensive, and budgets are limited, so the answer would be a phased migration. The first step would be to connect existing Modbus devices through secure gateways. This immediately enables the monitoring, analytics, remote access without ripping everything out. Then layer on modern tools like dashboards, and then over time, as devices reach end of life, you can replace them with more modern systems. So, like I said, that's going to be the last question I'm taking for today, but please feel free to reach out to me via email, and I can see if I can answer those offline. So I guess one last key message would be thank you so much for joining today. I really do appreciate your time. Just know that Modbus is not going anywhere, and it's really still a great protocol today. And I really enjoyed talking to you about the Modbus IoT Gateway, and I am very excited to see where the Modbus and IoT environments grow in the future. Thank you.